Hi everyone, and welcome to today's webinar, which is Better 2D Reinforcement Analysis with LimitState GEO. I'm Tom Pritchard, Principal Engineer here at LimitState, and I'm joined today by Professor Colin Smith, who is one of the originators of the DLO method that's underpinning LimitState GEO and also the LimitState GEO product manager. And Colin will be taking you on a step-by-step journey describing the process of modeling 2D reinforcement with LimitState GEO and demonstrating how it can lead to more accurate solutions than traditional analysis methods, while still being conceptually and practically straightforward. Today's webinar should last about 20-25 minutes, and there'll be time at the end for your questions, which you can put into the Q&A functionality that should be in front of you. We do try to answer as many questions as we can during the webinar, but often we don't manage to get around to all of them, but we will follow up where possible by email at the end of the session. Also, a recording of this webinar will be made available on our YouTube channel in the days following the webinar. So without further delay, I'd like to pass you over to our speaker today, who is Professor Colin Smith.
Okay, thank you, Tom. So by way of introduction to the software, if you've not seen LimitState GEO before, it's a fully general ultimate limit state analysis program designed to identify the critical collapse mechanism for any problem type in the form of a slipline mechanism, as you can see from these examples. In terms of the specific content today, we're going to be looking at modeling a basally reinforced embankment using two-dimensional geotextile reinforcement and giving a little bit of background to the software. As it's a short presentation, the main aim is really just to give you a flavor of what the software can do and how to set up a problem. Won't be time to get into the details of all the software functionality. However, as Tom has said, there'll be time at the end for questions. So let's look at the problem that we're going to try and analyze. It's a reinforced embankment. It's a 5-meter high embankment constructed from granular fill, founded on a soft soil stratum with linearly increasing strength of depth. We're going to put a reinforced geotextile base layer underneath the embankment. Geometry is available as a DXF file. We'll model a 5 kPa surface surcharge on top of the embankment, and we want to consider both internal and external failure modes. But LimitState GEO just does this inherently. It doesn't need to be told what the difference is. So just in terms of the soil properties we're going to use, for the embankment, we're going to use a more Coulomb material, a granular material, so it will always behave in a drained manner, 40-degree angle of friction, 18 kilonewtons per meter cubed unit weight. And for the base stratum, we're going to model it as an undrained clay with a undrained shear strength of 7.5 at the surface, increasing with depth by 2 kPa per meter, and unit weight of 15. And the geotextile model with a strength of 200 kilonewtons per meter and adhesion factors on the top and bottom of 0.8. Now, if we wanted to analyze this problem, a common approach would be a sort of slip circle method of slices. And this works well for many cases. However, it may not capture the critical mechanism depending on the geometry of the problem. Whereas LimitState GEO is able to identify the critical collapse mechanism for a very wide range of geometries. So let's see how we would build up this model in LimitState GEO. So we're going to flip to the software. So when you start up the software, this is what appears. And we're going to build the core model first without the reinforcement from the DXF file. Then we'll put in the soil properties and boundary conditions, see how well that performs, and then we'll add the reinforcement later. So first of all, I'm going to click File, Import Geometry. And I'm going to pull in this DXF file. We get a dialog that just allows us to amend the geometry a little bit before, but we're just going to take it as is. So that brings us the sort of geometry that we're going to start with. There are some construction lines in that import, these dashed lines here. I'm just going to clear those by right-clicking with the mouse to bring up that dialog window. And then we need to define our soil properties. So I can do this using the tools, create new material. I want a more cooler material. So for the embankment soil, give it a name, embankment. Might give it a different color, say that one. It's okay there. That's always drained, and it's got a strength of 40 degrees and a unit weight of 18. We're just going to assume that the water table doesn't play a part in this, so we don't need to set the saturated unit weight. Yeah. So that's that material generated, and I can, you'll see that it appears up here in the Materials Explorer. So this window on the left is shows us all the materials that are available to us. Some are predefined in the software. This is one we've just defined. But if I click on it, anything I click on, its properties appear on the right. So we can see the properties that we've just defined. And we've got, yeah, the strengths there. And I can just simply drag and drop this where I want it. So I'm going to put it there. And then I'll just quickly create the next material. Again, a more cooler material for that soft soil. Give it a slightly different color. That's going to be always undrained. We'll give it its strength of 7.5. And its unit weight already has a 15 there. Now we need to define the linear variation of strength separately. So I'm just going to create that material, click OK, and you'll see it appears up here. And if I click on it, I can see its properties over here. And I want to set this CU gradient property. And anything I click on here, you get a little bit of help dialog down in this window that explains what that parameter is. And if you need more help, it was a hyperlink to the manual. So the gradient we said was 2. And this datum term basically tells you where the initial value starts. The initial value is a 7.5, and that will start at the height of 0. So just need to check on the problem where that is. So if I click at this level, which is where I want it to be, I can see that that corresponds to a y-coordinate of 0. So we've got that set correctly for our datum. So that's okay, and I can drag that over there and drop it in. And I can also check what the strength is. I can use this facility analysis, preview strength. The short-term strength will give me the undrained strength. And if I hover over it, you can see that the strength just at that interface is 7.5. And then as I go down, it's increasing as we go down with depth at that gradient of 2. So that's just useful to check that you've got the settings right, particularly the datum right. We then need to add in some other properties. So we need some boundary conditions. We're going to model, we weren't told how deep the clay layer is, but we're going to assume that it perhaps extends very deep, but this will do for the model itself. So I'm going to click on these boundaries, and again, its properties appear here. I can change the support type. We'll make those fixed. And then if I click on this upper boundary here, I can define our surface surcharge. So we've got loads here. We've got a variable surcharge of 5. And we're going to apply some Eurocode factors in a moment. So I'm going to assign this as an unfavorable action. We'll come back to this setting here. This is a nodal density setting. It basically controls the accuracy of the solution. We'll talk about that a little bit later, but I'm going to set that to fine. We're going to ask the software, we can ask it a question: how much larger does a load have to be to cause collapse, or how much weaker does the soil have to be to cause collapse? So we're going to go for that mode in this particular case. And finally, we're going to apply some Eurocode factors. So we use what's called the scenario manager here. And I don't have time to go through it in great detail, but essentially we've got pre-programmed the DA12 factors, which are likely to be the most significant ones for this type of problem. And you can see if you're familiar with Eurocode factors, that's the sort of thing we have there. So they will be automatically applied. Okay, we should then be in a position to analyze the problem. So we haven't got any reinforcement in, so we're just useful to see what the situation is in this scenario. So the software will home in on the critical collapse mechanism and tell us how close to collapse we actually are. So you can see the mechanism is basically the edges of the embankments are going to kind of slide off in a sort of slip circle mechanism. And we get an answer in terms of what's called an adequacy and strength. So what does that mean? Well, if I click on the answer, we get a little table that tells us. So we get a list of the strengths of the material that we had originally, their characteristic values. They have been factored by the Eurocode factors to give us these values. And then the software is telling us that actually these are too low. You have to divide them by this answer 0.7 in order for the system to be stable. So basically this thing would just collapse at the moment, and the soils need to be stronger. In fact, they need to be back slightly above their characteristic values for this thing to actually be stable. Okay, so that's initially setting up the problem. Now we need to look at how we can make this more stable by including some reinforcement. So we're going to jump back to the presentation, just say a little bit about modeling reinforcement. So if we have some two-dimensional reinforcement in an undrained soil, if we were to try to pull that out, then we would be generating shear stresses on the top and bottom boundaries. There'd be a function of the undrained shear strength of the adjacent soil, and normally we assume an adhesion factor to allow for the fact that we're shearing reinforcement on the clay rather than clay on itself. And that alpha factor is usually between 0 and 1, or always between 0 and 1. So for a length L, the pull-out force will be 2 alpha Cu L, the number 2, because we're counting for both the top and bottom faces of the reinforcement. For the drain case, it's very similar, that we can calculate the shear stresses if we know what the normal stress is, and the shear stress will be the normal stress sigma n times tan phi. Again, we have this adhesion or interface friction factor. And again, the overall pull-out force for any given length would be 2 again for the upper and lower faces, alpha, sigma n dash, tan phi dash L. The issue here is how do you determine sigma n dash? In sort of typical hand calculations, you'd estimate it based on the weight of the overburden above the reinforcement. But of course, if failure is occurring, the stresses may well change as you mobilize the strength of the soil. So LimitState GEO does take account of that and uses the actual computed normal stress arising in that failure mechanism rather than an estimate based on overburden. So this problem, we're going to be putting a reinforcement layer between the granular material and the clay material. Actually, it's the other way around to this diagram. We've got the clay below and the frictional material above, but it doesn't really matter for what we're talking about here. So again, the software handles this inherently. If we've got a different material above and a different material below, then it will work out the pull-out force as written here. And if there's differential movement of material above and below, it will take account of that. So if you've got sliding above but no sliding below, then it will only pick up the full alpha Cu on the above. And then finally, the software can model tensile failure in the reinforcement because the software is based on plasticity theory, rigorous plasticity theory. It's going to model a ductile failure of that, but again, it can represent that. So when the specified strength, the tensile force in the reinforcement reaches that strength, then it will be modeled as effectively stretching in a ductile manner. And then finally, just to say that the software will pick up all kind of interactions. So here's a little shot of a reinforced slope, or maybe if you've got a reinforced edge for an embankment that where you're reinforcing up the slope. we can get different movements above and below the reinforcement. We can have the reinforcement pulling out of the soil, so the wedge of soil is sliding and it's dragging it out from this stable area. Here we've got the reinforcement actually failing in the ductile stretching mode, and here we've got enough reinforcement anchored in the material behind that the wedge itself moves past the reinforcement rather than dragging it out. So all those modes are inherently captured. Okay, so how do we specify reinforcement in the LimitState GEO? In the software, we have a special material called an engineered element, and we just pick that and select the specified tensile rupture strength, and then we can put interface materials above and below the element using an appropriate alpha interface factors. And these are implemented using what's called the Mole-Coulomb derived material in the software. And then we assign those to the same boundary, effectively the boundary between the embankment and the soft soil. So we'll show you how that is done in a moment. So just a reminder, these are the properties of the geotextile: rupture strength of 200, adhesion factors of 0.8. So we'll go into the analysis. So we'll hop back to the software. So if I click this button, that will unlock the project and allow me to edit it. So I need to define a geotextile property. So again, at the tools, I can create a new material. This time I'm going to pick an engineered element, which is a generic material that could be used to model a range of 1- and 2-dimensional reinforcement materials. For the application, I'm going to pick geotextile here. I'm just going to call my material geotextile. Give it a different color, it's red. And I don't need to set any, the only thing I need to set here is the rupture strength, which is going to be 200. That goes in there. Okay, there's already a predefined material with some default properties, so I'm just going to call that geotextile 1. And we're okay. So you can see again it appears here. Then I can assign it to that boundary as such. So it's now put there. I also need to create these interface materials. So again, create a new material. This time we use what's called a derived material. I'm first going to create the material that goes on the upper interface of the geotextile. So this is to take account of the alpha factor. I'll leave the color as is. So we refer this to the parent material. So the parent material is going to be my embankment material. And what I want is for its strength to be 0.8 of the embankment material itself. So that's created. And then I'm just going to create the lower material. The same process. A slightly different color. Oops. Its parent material is now the soft soil. And again, we've just got the same coefficients, 0.8 in these cases. So that's created. Now to assign those, what I need to do is click on the boundary itself. And if you look in the property editor here, you can see that we've got top and bottom materials. And if I click on this box here, a little button pops up here called change, and then I can pick what I want. So I want to put the upper interface obviously on the top. And then if I click on that boundary again, and here I want to pick the lower interface at the bottom. And if I zoom in, you can see that they are now there. We've got the green material and the purple material above and below. So we've now got our reinforcement all assigned. And we'll run the analysis. So again, we just click solve here. The software will work out the new stability or new critical collapse mechanism for this geotextile. So you can see the mechanism is much wider. Basically, the embankment is going to end up settling more as a monolithic mass and compress us all there. And we've got an adequacy factor of 1.042. If we animate that, you can see, hopefully, yeah, the kind of failure. So it's been the geotextiles folding at the corners, but basically the fact we've now got that there is allowing the whole thing to act more monolithically, and we've got an adequacy factor above 1. Now, if the adequacy factor is above 1, generally that means that the system is stable. If it's below 1, it means it's unstable. And in the context of the Eurocode or applying partial factors, if it's above 1, then you're complying with the code. If it's below 1, then you're not. So if we click on that again, basically we're just above the value of 1. So we've already applied Eurocode partial factors, so that's fine. We comply with the code. And in fact, the design values are a little bit higher than they need to be for stability. So that's all good. Our geotextile has done what it's intended to do. And when we analyze it, you'll see these bars appear. So this allows us to investigate what's going on in the geotextile itself. And here it's saying that the axial force is just below that 200 that we specified. So we're not actually failing the geotextile. Because the software adopts effectively a rigid plastic model of materials, if the material itself isn't failing, then the values that it will display there can vary a fair bit. So the best way to use the software is actually to set the strength of the material that you're actually using and get the software to tell you whether that is failing. But we could go a little bit lower the strength and we'd get pretty much the same adequacy factor. Very quickly, we can show that the software is obviously picking up a sort of a slip circle mechanism here, but we can pick up other issues. So one reason why that reinforcement is working so well, it's not working in this case by membrane action, it's just obviously for failure to occur around the geotextile, that's taking out energy from the system. It's also preventing the embankment failing on the surface. If I were to replace this top material, if the embankment was simply sliding on the our original soft soil, rather than on the geotextile, so if it's sliding on the geotextile, we're getting that sort of frictional interface, an extra strength. But if the geotextile wasn't there, but the soft soil was remaining sort of monolithic, then we would just get sliding on that surface, and we'll see that in a moment. Hopefully we'll just get a sort of corner failure of the embankment as we iterate to the final solution here. Yeah, so we're getting quite a simple failure here. Basically, the corners are sliding off the embankment. Okay, hopefully that's given you a quick demonstration of how we'd set up that kind of embankment problem. What I'm going to do just to wrap up is just tell you a little bit about how the software works. So it's based on a technology called discontinuity layout optimization, which can be used to provide rigorous upper-bound plasticity solutions. And it's a rapid and direct means of analyzing the collapsed state. And it's quite simple to explain. So we start off with a rectangular domain here for load on the surface and fixed boundaries to the left and the bottom. It's not a finite element method. Instead of using elements, we use a node-based formulation. So we populate the domain with nodes. Here we're only using 12 nodes, 3 by 4, but normally we're using thousands of nodes. In principle, we connect every node to every other node with a potential slip line, and then we use optimization to pick out of that set of slip lines. So that will be 12 times 11 over 2, 66 slip lines out of that set. Optimization can be used to pick out those slip lines that give us the critical collapse mechanism. which are these 6 slip lines. And again, the software, as you've seen, can work with many nodes and thousands of slip lines to give us effectively a wedge failure mechanism, but using thousands of wedges, and all according to classical plasticity theory. One of the nice things about the method is that it handles singularities inherently. This is often can be a challenge for finite element type methods, but often you see this in ultimate limit state collapse problems where you get all these slip lines meeting at a point. That's a mathematical singularity. As I said, is inherently handled by the software. Okay, so I can see we're running towards the end of time. So just to summarize then, hopefully you've seen that reinforcement modeling in limit state geo, we basically use the same mechanics as conventional methods, but we, such as wedge type analysis, but we allow thousands of wedges to be modeled. The software will inherently look at internal, external failure, pull-out links, reinforcement rupture, differential sliding on the top or the bottom of the reinforcement independently. And the software will automatically search all possible failure modes every time you solve. And again, hopefully you've seen it's very easy to use software. Hopefully a very intuitive user interface. We solve with one mouse click, easy handling of partial factors, and many other features I haven't the time to show you. And because it's so interactive, many of our customers use it to answer what-if type questions. You can play around with the geometry parameters very quickly and get a feel for the problem. What are the parameters that are controlling the design? And there's no need to impose idealizations or correction factors for non-standard geometries or pick a particular method of analysis. It's all the same analysis based on classic limit analysis, which is the mainstay of geotechnical engineering calculations. So that takes us to the questions phase. So if you've had any questions, haven't typed them in, please go ahead and put them in on the interface. So I've got a question: if the soil layer above the reinforcement moves with the reinforcement, can we actually mobilize resistance top and bottom? So if the soil layer moves with the reinforcement, then we won't be mobilizing that resistance, and the software will correctly model that. So it is able to model the situation where the reinforcement goes with the reinforcement. So it may be that the soil on top and the reinforcement both slide, and so you will mobilize resistance on the bottom of the reinforcement, but not on the top. But yeah, the software is set up to handle the top and bottom interfaces independently if needs be, but also that inherently deals with the classical pull-out type calculation. How could we add water above the soil? There's another question, so we're just going to bring the software back. So simplest way is to draw in a water table. So for example, this embankment suffered some flooding. I can draw in a, I've just got that in the wrong height. Let's try again. I'm not very good at this. So we could come in to here and then maybe have some flow through and then finish. So we've now got a water table coming through the embankment. I think the saturated unit weights that I set for these materials were actually reasonably realistic. So again, we can just run that analysis and it should tell us what effect that would have. So clearly that's going to make the granular soil weaker because we're going to deal with effective stresses. In fact, I'm going to halt that analysis because I think I've left that problem with the original incorrect interface. If I click on the water table, I'll see the water table properties normally, but I can click on this button, which will temporarily hide the water table. And I can click on this boundary and reassign what I want to the upper interface. Then I can turn that water table back on and we can analyze that. So yes, we should get a slightly weaker embankment material, but for the undrained analysis of the clay, it's not going to affect things. The water pressure itself, the weight of the water will obviously be applied differentially because we've got different water level. So we're getting an interesting mechanism here. Clearly, it's asymmetrical because we've got this gradient in that water through the embankment. And I think it's almost there. Yeah, so the adequacy factors come down a little bit, but not a huge amount, because I think most of the failure is in the clay. And again, if we animate that, we can see that it's heading off in that direction. I got another question. Can the software model it's a Tri-X geogrid? I think essentially, if you're happy to represent that as as I've basically put it in here, you're going to put in a rupture strength for it, and you can define upper and lower interface parameters. And yes, I don't know the specifics of that particular grid. And the second question is, would you include a geogrid in a slope stability analysis? So if we've got a platform that has a slope at one of its edges, if I'm reading that question right, then you can put reinforcement in at many different levels. You don't just model one in the software. You can put them in any way you like. So if you want to have, you've got an extended slope and you want to have reinforcement up the slope, then that can be inserted. So as long as you can represent those materials, as I said, the analysis that we're adopting in the software is very similar to the sort of classical textbook type analysis that you would use for reinforcement. So as long as you can do it in the textbook, you can do it with the software. Okay, I think that has taken us a little bit past time. So thank you very much for attending, and I hope you found that useful. I'm just going to pass back to Tom to wrap up the presentation.
Thanks, Colin, and thanks to everybody for joining us today. We do hope you found that useful. If you'd like to watch this webinar again, like I said at the beginning, there will be a link sent out to our YouTube channel in the next few days. So please feel free to share that link amongst people who you think might find it useful. You can download LimitState Geo from our website and use it in trial mode for a number of days. So please do visit limitstate.com/geo. And if you do have any questions that have arisen from this webinar, then feel free to get in touch with us via email on info@limitstate.com, and we'll be more than happy to answer your questions. Be sure to follow us on LinkedIn, because we'll be putting out notifications of future webinars, both for LimitState Geo and our other products, and you'll be the first to get them from that page. So lastly, I'd like to say just again, thank you to everybody for joining us, and we do hope to see you again for one of the future sessions. Goodbye.